Okay, welcome to Tectonic Cluster Topic 2 video series. This is the first video in the Topic 2 series. For this video, we'll be addressing the concept of impact of tectonic processes on magnitude of earthquakes. Right, so there should be 4 videos in this series to finish up Topic 2. Okay, hopefully breaking it into smaller bits makes it easier for you. So I believe you would have seen videos of what happens during an earthquake growing up until this point in your life. This is a typical video of what happens in an empty apartment. Actually, it isn't an empty apartment, but the apartment very much like maybe your living room or a living room you've been in before. Okay, with things that can be flung around as a result of an earthquake. Okay, this is an earthquake in Alaska. Right, I know Alaska is not a place that we commonly think of when we talk about earthquakes. Right, we always think of places like Indonesia, Japan, China, places in Asia that we're familiar with. But we have to understand that geographically, earthquakes can occur anywhere near crustal boundaries. Okay, so if you have a plate boundary that's active, and all plate boundaries are active, as we've covered in topic 1, you have a fair chance of experiencing an earthquake. So what are earthquakes? Earthquakes basically is the shaking of the ground, right, due to release of energy because of crustal plate movement. Okay, sometimes the vibrations are very very small, but sometimes they're very very large. We have no control over this. Nobody has the ability to control the magnitude of earthquake. Nobody can actually actively stop an earthquake from happening. Neither has it been proven possible to trigger an earthquake. Right, so as of today, human science has no technology to do anything with earthquakes except to experience it and to provide mitigation methods or to mitigate against the earthquake itself. Okay, so this is a very brief video on earthquakes. Very good video by National Geographic. Watch it in your time. Right, I will not go through this in the lesson itself. Now, when you are thinking about how earthquakes are caused, right, always go back to the idea that the crustal plates are moving, they're active, they are in a constant state of movement. And when this very large crustal plates are moving, right, and they're actually they're stacked against one another most of the time, whichever direction of movement you're triggering, you will trigger friction as the plates grind against one another, push against one another, or even as they pull away from one another, there will be some sort of grinding. Okay, so imagine you had an ant on the table and suddenly the table breaks into two, right? So the ant will suffer an earthquake. Okay, so on a similar scale level, scaling up, right, we are like ants on the earth that is the table that we're on. So when you are talking about earthquakes, there are some key terms that you need to have, geographical terms that you must have in your explanation to discern yourself from the person in the coffee shop, right? So when you're talking about the Earth's crust, right, the plate boundaries, these are called fault lines. Specifically, when you're dealing with description of earthquakes, these are your fault lines. Along the fault lines, right, you will have friction, you will have stress buildup, and sometimes when it overcomes that friction, right, then it will shift, it will snap, it will jump into a new position, and the resultant energy that's released in the occurrence of an earthquake is called seismic waves. Another key term you need to know. Okay, what do we experience it? We experience it as ground shaking, right? So the first diagram here, this first set here, is the final diagram that we learned in the previous topic under this cluster. It's a transform plate boundary with your two sides sliding against one another. So you take a look at the sequencing of this, right? You can see that as they tear apart, right, and they slip and they snap onto the new position, there's a lot of energy that's released. So if you're on the top of this crustal plate, you will experience this as an earthquake. So I want to bring you back again. Reminder, when we talked about this particular type of transform plate boundary, what was the phenomena that is experienced greatly by man? You do not see new landform. You do not see something that's created. You experience earthquakes. Right? A few more key terms. Three more actually. In the may aid you in the description of an earthquake. Focus is where the actual point of seismic wave release is. Focus generally, yeah, not always, generally is found in the crustal plate. Okay, generally is found in the crustal plate. Focus is matched right above on the surface level by a point called the epicenter. Okay, so if the focus is very near the epicenter, this is called a shallow depth earthquake. Okay, so it can be very deep in the crustal plate. It can be very near the surface, and this has an impact as well. Right? Fault lines, seismic waves. So two to add on to our earlier two. Okay, so if you have a deep focus earthquake, it means that the focus point is very much further down from the surface itself. If you have a shallow focus earthquake, it means that the focus, the point of where the epicenter is, no, where the origin of the earthquake is very near the surface. Right? What does this mean? Right? It means that if the focus is very near the surface, the energy is felt greatly by the people living on the surface. If the focus is very deep underneath the crust, then a lot of the energy that's released is actually absorbed by the layer of crust that's above it already. Okay, bear in mind the crust is although we call it a solid, right? It has some ability to absorb seismic waves as they move outwards. So as you make the seismic wave move further, the impact of it is lesser. So the deeper the focus, by the time it comes up to the surface, the waves come up to the surface, it has really lost a lot of its potency. So this is also why there are many occurrences of deep focus earthquakes that go unreported in Singapore news, because it is so deep focused. When we experience it in those regions like in Indonesia, right, it becomes negligible. Okay, so unless you have a seismograph, a machine that's tracking this, you wouldn't even know that earthquakes has happened. Great segue. What's a seismograph, right? Seismograph is a machine that measures the amount of seismic waves that's produced as a result of an earthquake. Okay, so this is a very bare bones description of what it is. Okay, so basically, it is able to um, feel the vibrations that are released by the earthquake itself, however small or however large, and is able to track it out on the graph. Okay, so not all seismographs look like this. Nowadays, a lot of seismographs do not have physical entities like this. They are digital as well. But this is a rough image of what a seismograph will look like. Okay, so when you have a seismometer or seismograph, it will be able to determine the magnitude or the size of an earthquake. Okay, so the magnitude is on a scale called a Richter scale, right? And with a larger number, it means the earthquake is more serious, right? Seismographs are installed actually globally around countries that are experiencing very high risk of earthquakes. Do we have seismographs in Singapore? We do, right? We do, because even though we are at very low risk of a wide or large earthquake impact, we will need to consider the impact of earthquakes in the surrounding area. For example, earthquakes that happen in Indonesia, very near us, and sometimes they do, as a result of how large they are, cause some sort of tremors and rumblings that can be felt in Singapore as well. Okay, so we do have seismographs, but if your country is plagued by earthquakes, you are lying along a very active fault line, then these are essential equipment that governments will put in place together with warning devices, so that if an earthquake is detected, the population can be warned. When you're looking at a Richter scale, right, a Richter scale, okay, it runs from 1 to 10, okay, 10 being the greatest ever recorded so far. So if you look at the examples on the SLS guide image here, right, correspondingly, 2011, the Tohoku earthquake was a 9. Okay, it was only a 9, right? And as you move up the scale, it doubles in the impact. It's not arithmetic, it's actually uh, at doubling an effect. Okay, so what would be a scale 3 like? Right, imagine the classroom desk that you have. If it's scale 3, right, the classroom desk will be shaking at a point where your untethered objects on the classroom desk would fall off. Okay, the desk will stay intact, but the untethered portions would fall off. What do I mean? It means your pencil case will fly off the desk. Okay, if you're at 4, your desk will be flipped. Okay, the vibrations are strong enough that your desk will be flipped unless you're holding on to the desk. Okay, so this gives you a rough idea of what you're looking at. Right, so once again, you have to remember that the magnitude, okay, the very large magnitude earthquakes don't happen very often, but they are very, very destructive. Reason being, it takes a lot more potential energy to be stored up before a large scale earthquake can happen when the slip happens. So if you are able to defuse, right, from a logical standpoint, if you're able to defuse all these little buckling, right, when the energy is being stored up as the plates slide against one another, you technically can lower the risk of having a large earthquake. Okay, but once again, there is no human tech that can do this at this current moment in time. So earthquakes cannot be controlled, right? It cannot be controlled. It cannot be predicted accurately, and it cannot be controlled. Okay, the moment magnitude scale is another scale like the Richter scale. Okay, but it measures the total energy released during earthquake instead of just the largest wave. So scientists over time have used this as a sort of a supplementary scale to measure the overall damage that a particular earthquake has caused. Okay, so based on this, it gives a sort of more accurate. It uses a better parameter for gauging the impact of the earthquake itself. So moment magnitude scale is another one, like the Richter scale, supposedly a bit more accurate because we do measure the total amount of energy release, unlike Richter scale, which measures just the highest one. Okay, so with that, we have come to the end of earthquakes and how tectonic processes impact the magnitude of earthquakes. So in the next video, we will be covering how tectonic processes impact the magnitude of volcanic eruptions. So once again, I would like to remind you the videos are embedded within the PowerPoint slides that are in your Teams. If you would like to see the, no, it's not like to, you have to watch all the embedded videos because they form another layer of examples of a different sort of stimulus in your mind, so you store in a different place in your brain, right? So I do not go through the videos in the content lectures, but you need to watch the videos. Okay, so I'll see you in the next video.